Hi everyone, I'm Shereen and I will be presenting our paper StreamReady, learning what to answer and when in long streaming videos. This paper is done in a collaboration between University of Central Florida and Microsoft Research. Streaming video understanding can be categorized into two types. Firstly, causal understanding, where the question depends on current or past events, making it pretty similar to offline understanding or like regular video understanding. For example, which team's player has started the match. Now, another type is proactive understanding, where the question depends on future events. For example, let me know when a goal has been scored. In this case, the model has to actually watch the evolving video to know when there is sufficient evidence to answer. The main issue is current models are largely answer content focused, so they ignore timing. That means often they answer either before the evidence or after the evidence. But for a mistimed answer, even if it is correct, it is still undesirable because an early answer often reflects speculation and a late answer hampers real time utility. Unfortunately, current evaluation metrics are also largely focused on answered content, and thus it treats both of these answers similarly, and models get rewarded even though it is a mistimed answer. Therefore, we introduce readiness aware streaming understanding, where the task is not just to answer correctly but also on time based on the visual evidence. Here is an overview of the framework. Firstly, it's a we start with task agnostic storage, where given a lot of certain amount of frames, they are encoded with a visual encoder and stored task agnostically, which means that we want to store everything instead of any reliance to the given question. Secondly, we perform task aware reasoning through the reasoning module through different levels of local and global level reasoning. And for answer timing, the evidence sufficiency is measured throughout the video coupled with the reasoning process, and the LLM is only triggered to answer when it has seen certain amount of evidence. Now, the task agnostic storage starts with a multi-level visual memory tree where each level is an abstracted version of the lower level. The lowest level contains short-term details and is updated by FIFO. And so once its size is exceeded, the evicted frames go to the next level. The upper levels are k-means initialized summaries of the lower level and updated by EMA-based clustering. So whenever a new feature arrives, it's merged with a cluster based on similarity. If not, it forms a new cluster. And whenever a certain question appears, the model actually moves from task agnostic storage to task aware reasoning through the local and global retrieval and local and global level reasoning. Now, since the reasoning representation encodes the model's evolving belief about the answer, evidence sufficiency or the model's readiness to answer a question naturally emerges from this representation. Thus, we introduce a learnable readiness token in the long-term reasoning block of the reasoning module. It looks at basically how the reasoning representation evolves over time, and an MLP head monitors this token and measures a score. Whenever that score exceeds a certain threshold, the LLM generates the answer. Otherwise, the model keeps watching the video for more evidence to appear. Now, to actually learn when to answer with respect to evidence sufficiency, we need supervision about what does it mean by evidence sufficiency. However, existing training data do not have that evidence annotation. Thus, we construct pseudo labels directly from the model's own representation. As the model observes more and more of the video, its internal representation becomes more stable. So we measure the similarity between the current representation and the memory. If the similarity is high, it means that the model has seen certain amount of evidence, so we treat that time step as a pseudo positive region. Otherwise, we treat it as a pseudo negative. We then use a contrastive objective to encourage the model to assign higher readiness score to pseudo positive regions than pseudo negative ones. This allows us to train the model even without needing manual annotation. Now, let's say we have our model that does on-time answers based on visual evidence, but how do we evaluate that? As we saw, existing evaluations only measures correctness. So we introduce ARS to evaluate timing. If a model answers too early before seeing the evidence, we apply a strong exponential penalty. And if the model answers too late after the evidence, then we apply a milder linear penalty. We then combine this with standard accuracy to define effective accuracy, which captures both correctness and timing, which we can see in this plot here, that even after applying the effective accuracy, even for models that had high raw accuracy, their performance dropped by a large margin after taking timing into account. Now, to actually properly evaluate on-time answering capability, we also need a benchmark that has annotated answer evidence window. So we propose ProReady QA with 5 proactive or feature-dependent tasks where the videos are from 30 minutes to 1 hour long, and it has about 5,000 QA pairs. We evaluate our model on 5 streaming benchmarks on the task of visual question answering and 4 offline video understanding benchmarks on the same task, and we report accuracy and ARS as the evaluation matrix. Here we show some representative results where we see that our model is the best in bridging the gap between accuracy and effective accuracy, and thus proving its on-time answering capability. Now here we show that starting from the baseline, incorporating task agnostic storage and task aware reasoning increased the accuracy. However, the ARS remained mostly similar as the model still did not have any notion of evidence sufficiency. When the readiness monitoring system is included, the ARS drastically improved, showing the effectiveness of the process. And lastly, here we show that with our lightweight readiness monitoring system, our model can keep both the reasoning cost and latency minimum compared to previous methods. Thank you for listening to me. For more details, please visit our paper.